So, hi, hello everyone. This is Ruturaj. I am here to explain something about the quantum search. So there are two terms that I can see in front of me. That is, there is the first is the quantum, another is the search. So we know that about the classical search and heuristic search. So what about the quantum search? So let's dive deep into this. So what kind of contents that I am going to cover in this section is the first definitions and its working principles, how the quantum search works and what kind of definitions it has, then what kind of algorithms used in this. And then I will talk about little bit deep into the Grover's algorithm and its functionality, then its implementations in Python. Let's talk about its definitions. So quantum search is a technique in the quantum computing used to find a specific item in an uncertain database faster than the classical methods by using the quantum properties like superposition and interference. That means it is clearly showing that the quantum search is completely different from the normal computing which is used, and it is used in the quantum computing. And why it is called as the quantum? Because it uses the quantum physics concepts like superpositions and interference like things. And as it is using this technique using the superpositions, entanglement and interference to evaluate possibilities simultaneously. So here the search occurs simultaneously, not sequentially, offering the quadratic speed up. That means over the classical method. Here the classical methods is little bit slower than the quantum search, which has the complexity On of n order complexity. But here the quantum search has less complexity, space and time complexity than that of the classical methods. Now to explain these, what kind of quantum behavior, just like superpositions, interference, how it is going to help me to search um, in this quantum computing, I'm explaining by this a uh, puzzle path. Suppose there is agent which is starting from this triangle, and that agent has to reach here, this golden button. Then that agent start from this way and moving to this, and at this point it has two paths. First this, second is this path. As there is two paths, so that agent, when in terms of classical search, it will find individual path sequentially. That means it will go first in this path, then it will go first, then it will go second in this path. So again while moving to this path, it will encounter another two ways. One is this, another is this. So it then first sequentially move to this path, and if it is stuck, then it will move towards this path. So here in classical point of view, that agent is searching each and every path sequentially. So first moves in the one path, if it fails then moves in the another path, if it fails then moves into the other path. So that kind of things will happen when we talk about the classical path. But when we move in a quantum search, then after reaching this position, suppose I am taking about after reaching this position, uh, here I will encounter two paths, then this agent will have its two copies. One will move in this path and another will move in this path simultaneously. Whenever two paths will occur, the agent will have its own copy move in the two paths simultaneously. If they will move simultaneously, so they can search both the paths or multiple paths simultaneously at the same time. This phenomena is called as the quantum superposition. So to explain these things, I have included a video in the next slide. Let me show it.
In a normal search, our agent tries to search every path randomly to reach the destination, and we cannot claim that the path we find is the shortest until we visit the entire search space. However, with quantum search, you start with one agent, but whenever the agent encounters multiple paths, we send one agent to each new path. This allows us to search more quickly. The twist in this situation is that all those agents you see on the screen are just one single agent in multiple places. This phenomenon is known as quantum superposition. At the end, when we find the solution, all the other agents disappear, and the real existence of the agent is at the destination. It's strange, but that's how quantum computers are going to work. When we compare agents, we can see that quantum computers can easily win. Even with an increase in problem size, the complexity of the problem for a quantum computer will be linear.
So as we have seen that the quantum search is the most efficient way as compared to the classical search. So here are some key differences between the classical search and quantum search. So when we talk about the time complexity, there is a nth order, whereas in the quantum search, the complexity in terms of root over of n. And we are giving example that is the linear search, whereas in quantum search, the Gruber's algorithm is followed. Speed, classical search is slow for the large data, whereas in quantum search, it is much faster than the classical search. We can also have the differences between the quantum search and the heuristic search. Here are some basic key differences. That is, heuristic search uses some rules, thumb rules, or estimate to find the best path, whereas the quantum search uses the quantum mechanics to search the faster way. So, heuristic search is based on artificial intelligence, whereas the quantum search based on some quantum computing concepts. The working principle of heuristic search is the heuristic functions, that is consistent HN, whereas the quantum search, that is superpositions and interference, quantum superposition and interference. When you talk about the complexity, the heuristic search complexity varies, not fixed. That means heuristic search is a smart way to approach to the different algorithms. But in quantum search, it is always root over of n. When you talk about the hardware, heuristic search is a classical computers, but for quantum search, it will be needed a quantum computers. Accuracy, heuristic search may not guarantee optimal solutions, but quantum search, high probability that the correct solutions will be get. So now these are some examples of the heuristic search algorithm and quantum search algorithms. Now what are the algorithms basically used in the quantum search? First is the Gruber's algorithm, Siemens algorithms, Deuce algorithm, and the Deuce-Jose algorithm. There are other algorithms are also there which follows the Gruber's algorithm, that is the amplitude amplifications, quantum counting, quantum work search, and the Duhr-Hoyer algorithm. Now, basically, most important algorithm and most fundamental, which is most important, that is the Gruber's algorithm. Let's talk about the Gruber's algorithm. Gruber's algorithm iteratively boosts the probability amplitude for the target item in an unstructured database, moving from uniform superpositions to a high probability state, visualized as a quantum state vector rotating towards the solutions. Stepwise, amplitude of the solution increases while other decreases, reaching the maximum probability in a roughly, that is the complexity is root over of n by m iterations. What does this mean? Suppose we have many states with us, and this is suppose our target state, and we need to find this target state t, and others are also present. So Gruber's algorithm does that the amplitude of the target state increase and the remaining amplitude of the other states will decrease. So Gruber's algorithm does these kinds of phenomena. And to do this, there are two kinds of main functionalities present. One is the inversion and is the diffusion. Let's talk about the two steps briefly. So this is an example where I have given that in the example chosen random values between 1 to 100. So if we have 1, 2, 3, 4, just like to the 100, then suppose I have to choose the 49th term, then in the worst case I will have 1 by 100th chance of success and a 99 by 100 chance as failure. So for the worst case I will have 99th failed attempt. But in the quantum search there will be 100 root 100, that is 10. In the 10 runs I can find the solutions. So here the complexity and the number of n graph is shown, where I can see that there is root n complexity order for quantum search, whereas for linear search there is a linear graph, and for other search there is n log n square complexities are there. Now let's talk about how this Gruber's algorithm functions in the quantum mechanics purposes. Suppose here I have n states, that is from 0 to n minus 1, and each states I have noted as 0 states from 0 to n minus 1, and this can be represented as this. That means I have n number of states, n number of 0 states. So I can write all these states as the superpositions of each and every individual terms, each and every individual states. That is S equals to psi naught 1 by root n summation of x. X represent each and every states. That means this equation represents that here each and every states are present simultaneously at the same time and having amplitude that is 1 by root over of n. Suppose I have a target state t to find this target state, and that is represented as get t. So I can represent this as 1 by root n summation of target state and all other remaining states. And it is also can be represented as this, whereas alpha naught summation of remaining states plus beta naught remaining into target state, where remaining states is not equal to the target states. Here the amplitude of all the remaining states is 1 by root n and target state is also 1 by root n. So if I represent this graphically, so remaining states and target states by taking at x-axis and y-axis, so the superposition state will be in the middle making an angle theta naught. So here both amplitude are same, that's why it is going in the middle of the x-axis and y-axis making an angle theta naught. Now let's discuss briefly the two states. Those are the inversion and diffusion states. Let's call it as inversion about x-axis. So inversion means there is an inversion operator involved, that is I minus 2. This is called as the external multiplication or external product of the target states. And what it involves? So inversion means we know that this is x-axis, this is y-axis, this is remaining state and this is the target state, and the y naught, that is our superposition state, is going in between the t and r. So we are taking the inversion of psi naught about the x-axis. That's why this is the new result occurs after the operator, after the operations of the inversion operator. So inversion operator is nothing but the IT, when it is operated on the psi naught, it will inverted the magnitude, especially the magnitude of the I, magnitude of the I coordinate. So when we have taken the psi naught, alpha naught r plus beta naught t, when we operate it on the psi naught, it will just invert our target state. It will just invert the amplitude of our target state. So making it from plus beta naught to the minus beta naught. It will just, so we have inverted the amplitude of the target state. That means we have marked our target state. This is our target state. Now after inversion, we'll go to the diffusion. Here in the diffusion state have this operator, that is from minus HA, minus HN I naught HA, and HN is the Hadamard operator, which will again operate on this I psi naught and will give the final output. So that means here IT psi naught again operated by the D, that is the diffusion operator, which will be inverted with respect to the psi naught. This is the thing, this is the 2 theta naught. So that means inversion is again takes place with respect to the psi naught. Which is inverted? This is inverted with respect to the psi naught, making an angle, which is making an angle 2 theta. Then the new vector which will be operated, that is the final output, will have also an angle of 2 theta with respect to the psi naught. So here we can see that in after the diffusion operator, our the new vector we find that is moved towards our target output. Here we can see our target output is now here the final output is now close to the target output. Now after these kinds of operation iterations, after 2 3 4 iterations, we can have our target output, only magnitude of the target output, and others will be gone. See, suppose we have taken a 2 qubits process where I have taken 1 as my target output. So in the first operations, we have inverted our target output. The magnitude of the target output is inverted, and others are at the same situations. And then again we have taken the mean average inversion, amplitude inversion, amplifications of the mean average. After getting that, the magnitude of our target output increased, whereas other are vanished. There is no other states present, whereas our target output has the maximum amplitude, that is 1. So this is achieved by number of iterations, not we can achieve also in single iterations, but this can achieve also number of iterations. Now what are the quantum circuits are involved in the Gruber's algorithm? The first is the Pauli X gate, that is it changes the 0 state to the 1 state or 1 state to the 0 state. That means in the basic electronics, it acts as a NOT gate, that is convert from 0 to 1 or 1 to 0. Now when I talk about the controlled Z gate, it flips the phase target state to mark it. That means when we will have 0 as a target state, then it will make it as the -0. Or if you have 1 as the target state, it will mark it as the -1. Like the previous one, where I have target state as 1, the first inversion takes place where it flips or it changes the magnitude towards its negative format. It is just like that. The control Z is forming this. Then the final is the Hadamard gate, that is represented as this. The inner product of H Hadamard conditions for the nth order. It converts the definite state into superpositions. What means of superposition is, that means when I take a single qubit thing, it will convert it the superposition of 0 and 1. That means for single qubit, it will convert the state to to this. And for a 2 qubits, it will convert the superposition, it will convert the state into the superpositions of 0 0 0 1 1 0 and 1 1. Now let's get to the gate structure. The complete group structure will be like that. For 2 qubits, let's suppose my target state is 0 0. I can represent as this, that is 0, and making it a 2 qubits. So for inversion operator, I will have X gate, 2X gate, and in between there is a Z gate. And for a diffusion operator, 2H like this, here 2H gates are present. That's why around this inversion operator, we will have H gate, means Hadamard gates. These are X gates, Z gates, and another is the Hadamard gates. By combining these two things, we will have the complete circuit. So this is the Grover's algorithm graphical or circuit representations, where I have taken single qubits to the nth order, to the nth times. That means there are n states of 0, where each and every states are represented as under Hadamard. Then this is the unitary, where X and Z gates are present. Then it is again going to the Hadamard. Then this is the diffusion operator. Then again Hadamard, and it is repeated to the root over of n times. That means the complexity is root over of n. Now if we talk about the implementation in Python, then let's go. We have here in the Google Colab applications of any kind of Grover's algorithm. So here we have installed a Qiskit, and from that Qiskit we have imported the quantum circuit. Then I have created a 2 qubit circuit, that is a quantum circuit 2 qubits of 2 cross 2. Then first apply the Hadamard conditions. You can see that step 1, I have for the superpositions, that we need to have a superpositions of 2 qubits by taking the 0 and 1. Then step 2, oracle is present, where I have taken the target as 0 1. First X gate is applied, then controlled Z gate is applied. Then you can see that then again X gate is applied, which is for the inversion operator. Then after that step 3, which is called as the diffusion operator, I have taken first Hadamard gate, then X gate, then again Hadamard, then control X, and then Hadamard. All the things that we have seen in those PPTs, all I have done in this kind of here. Then I have measured this, simulate this, and compiled circuit. Then lastly, I found the result as my target, that is 0 1, which we have taken here. So here are all the things that we have. Thank you.